Yeah, it's recording.
That's right.
Hi everyone, today we will be talking about our implementation of a hybrid PID controller. So traditionally, PID controllers are widely used in a lot of industrial processes like temperature or pressure control, simply because of their simple structure and how robust they are. The controller that we will be looking at today replaces the PI controller with a two-input fuzzy logic control, or an FLC, and also executes the derivative part of the controller in incremental form. Because we are doing a PID controller, our hybrid PID controller employs a classical controls technique. Some of the features of our controller are that it's easy to implement. The gain tuning is done with a genetic algorithm, and our controller is able to handle high nonlinearities of complex systems. So what exactly is a fuzzy controller? Essentially, fuzzy logic is meant to mimic the way that humans think, because oftentimes things aren't as black and white. So, for example, when we talk about the temperature of water, we don't always just characterize it as hot or cold. Um, Sometimes we talk about it as being extremely cold or a little bit warm or lukewarm, and that's kind of what the fuzzy logic controller tries to mimic. So, putting this into the context of the automatic braking system of a car, on the first picture on the top right, we see that the distance between two cars is characterized as either close or far. And as soon as the car passes from the far zone into the red zone or the close zone, brake pressure is applied accordingly. So once the car moves into the close range, high brake pressure is applied, but that's not always what we need. We don't always need that high amount of brake pressure. That high amount of brake pressure could be detrimental to the car and also the passengers inside. So this is where a fuzzy logic controller would come into play. Instead of characterizing the distance between the two cars as either close or far, we can characterize it as a range between close and far. So this way, brake pressure can be applied proportional to the distance between the two cars. So some of the advantages of a fuzzy logic controller is that you'll get a much smoother output. Um, and it also deals with nonlinearities of complex systems, like I mentioned before.
So a derivative controller essentially responds to a change in error with time. And the reason why a derivative controller is a good component to have within an overall controls technique is it has a good transient response time. For example, on the right, you see a step function, and the output is very quick to respond and rapidly moves towards its input. Integrating a fuzzy logic controller into a conventional PID controller, the fuzzy logic controller maps the entirety of the input space to an output space, which can kind of be seen in the example on the right, where you have an input space. That input space gets fed into a black box, in this case, our fuzzy logic controller, and then that is mapped to an output space. And then looking at the block diagram on the bottom, you have an E and delta E that's fed into the fuzzy logic controller, and you get an output U. The logic controller is also constructed using natural language, as we will cover in the next few slides.
So in order to pass in those errors to the fuzzy logic, we have to normalize those state errors into the range of -1 to 1 for the FLC to process. And those factors are defined as below. For this example, we choose a relatively simple plan system for our testing plan so that we can see how the fuzzy logic work. The model is basically 1 over s plus 1 as a transform function, and we have the coefficients of C, L, and T, which respectively are gain, the system gain, time delay, and the time constant. So now we're going to construct our type 1 fuzzy logic controller, we mainly use the MATLAB fuzzy logic toolbox, and it allows us to build the membership functions using like natural language, like negative, 0, and positive. So we can map the output as like negative big, negative medium, which are the states that's like within the 3 inputs that we already know. So finally, we need to construct the rules based on the strings, that's like what it showed in the right side of the slide. So if the error and the derivative of error is equals to something, then that is belongs to specific states in the output membership functions. And one thing to notice is for different problem, the user could always set up the membership functions as they want. Like what we said in the previous slide, we have like a car braking system, then it could be like close, very close, or not too close. So here's how the FLC being constructed in a graphic representation. So we have the degree of membership in the triangular distribution form, which is similar to what the paper was talking about. And when we plot it out in a control surface, it's a pretty smooth surface that shows us our control space for both error and the derivative of the error. So now we're gonna introduce the type 2 FLC, which is included in the MATLAB toolbox that we're just like want to see how good it's performed than the type 1. So what's different from the type 2 is that it adds a boundary to the type 1 FLC, and those boundaries would allow the controller to handle signal uncertainties that is being passed into the controller. So the constructed fuzzy logic plot would be kind of different because now we have a upper bound and lower bound being specified. And as you can see, the control surface now being more like nonlinear, and it should be performed difference when we test out the model. So we'll see in later slides. So here's the Simulink model that we have, and we compare 3 controller. The first one is conventional PID, and we have the gains that's tuned by the MATLAB built-in function. So it's pretty simple, like the proportional gain, integration gain, and the derivative gain. So the next 2 is the type 1 and type 2 fuzzy PID. As you can see, the error is being passed in and being multiplied by the normalizing factor, then pass into the fuzzy interference system, and finally output to the factor that's factoring the fuzzy logic output to what the system scale is. So here's the result of 2 different plane model. The first plane model is the nominal model that we have those 3 coefficients set to 0.5, and it's obvious that the FLC, both type 1 and type 2 FLC, performs better than the PID in the perspective of looking at the overshoot and just the travel path. Even for the modified model, we have a better, a lower overshoot from both FLC controllers. So here's the statistics of how the controller responds to the step. So even the PID has less absolute error, it has a way larger overshoot to the overall controller, like the controlling time. So we considered that the fuzzy controller could perform better in other problems as well, because this is just like a very simple 1 input 1 output problem. when the problem becomes more complicated, then we should expect that the FLC would be performing way better than the PID controller.
So we found for our implementation, our hybrid fuzzy logic controller outperforms the PID controller, particularly with respect to settling time and overshoot. These natural language rules that we use in our fuzzy logic controller are applicable to many commonly encountered problems, such as temperature control, or even car braking like Sneha used as an example at the beginning. One potential challenge is this schema convergence depends on our closed loop time constant tau sub c, which could be challenging to adjust for some other transfer functions if we did not use 1 over s plus 1. And in place of the genetic algorithm that this paper proposed using for gains tuning, we used the MATLAB PID tune function. Since this method was developed after this paper, and we hypothesized that this tuning method would be more effective than the genetic algorithm used in this paper.
So
That's all.
yeah, thanks for listening. That's all.